Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Hello everyone. I'm excited to explore the topic of Bayesian optimization for adaptive experimental design with you. To begin, could you provide an overview of what Bayesian optimization entails and how it fits into the broader context of experimental design methodologies?
Bayesian optimization is like having a smart friend who helps you find the best toys in a big, messy toy box without having to dig through it too many times. When you want to find the best toy, you can't see all the toys at once, and some toys might be hidden or hard to reach. So, instead of pulling out every toy one by one, your smart friend remembers which toys you've seen and how fun they were. In the world of experiments, this toy box represents complex systems or problems where we can't easily see or measure everything. Bayesian optimization helps scientists and engineers make decisions about where to look next based on what they already know. It works by creating a model, like a map of the toy box, that predicts which areas might have the best toys and how uncertain we are about those predictions. This method is especially useful when experiments are expensive or time-consuming, like when designing new materials or products. Traditional methods might require a lot of attempts to find the best option. But Bayesian optimization does a better job of using the information from previous tries to make smarter guesses about where to explore next. Overall, Bayesian optimization fits into the larger picture of experimental design by offering a way to efficiently navigate complex problems and make informed decisions without wasting resources.
That's a great analogy. Given this understanding of Bayesian optimization as an efficient navigation tool for complex experimental design, can you elaborate on how prior knowledge is integrated into the Bayesian optimization process? How does this aspect enhance the overall efficacy of the experimental design compared to traditional methods?
Integrating prior knowledge into the Bayesian optimization process is like using a treasure map that gives you hints about where to find hidden treasures in a vast area. Before you start searching, you might already have some clues or information about where the treasures might be located based on past experiences or research. This prior knowledge helps you not waste time exploring places that are unlikely to bear fruit. In Bayesian optimization, this prior knowledge is used to create a model that helps predict where the best outcomes might be found. As the experiments progress and more data is collected, the model continuously updates itself, becoming smarter and more accurate. This is different from traditional methods that often treat each experiment as a fresh start without using what was learned before. By incorporating prior knowledge, Bayesian optimization enhances the experimental design by allowing for more informed decision-making about where to focus efforts. This approach not only saves time and resources, but also leads to quicker discoveries by efficiently navigating the design space. In contrast, traditional methods may require many more experiments to reach the same conclusions, sometimes leading to unnecessary costs and delays. Overall, the use of prior knowledge in Bayesian optimization makes it a powerful tool for tackling complex design problems.
That's an insightful perspective on the importance of prior knowledge. Moving on, could you discuss how Bayesian optimization handles high-dimensional optimization? What challenges does high dimensionality present in experimental design? And how does this method effectively address those challenges?
High-dimensional optimization in Bayesian optimization can be compared to trying to find a hidden treasure in a vast field filled with hills and valleys. If there are too many hills, dimensions, it can be really hard to find the treasure because every little bump can look similar, and you might not know where to dig next. The challenge with high-dimensional spaces is that the more dimensions you add, the more complex the landscape becomes. There can be only a few high points, good solutions, surrounded by many flat areas that do not help you find the treasure. Traditional optimization methods struggle in these cases, because they often need to explore these flat areas extensively, which is like wandering around a huge field without any clear direction. Bayesian optimization tackles this challenge in a few clever ways. One strategy is to focus on reducing the design space by identifying which dimensions, or variables, are the most important. This is like deciding to only search in certain sections of the field based on prior knowledge of where treasures have been found before. Another method is to break down the big problem into smaller, simpler problems, making it easier to navigate through the complexity. This can be compared to dividing the field into smaller plots to search one at a time rather than trying to explore the entire area at once. Additionally, Bayesian optimization can project the high-dimensional data into a lower-dimensional space, which helps simplify the landscape. This is like flattening the field so that you can see the hills and valleys more clearly, allowing you to spot where the treasures might be hidden. By using these approaches, Bayesian optimization effectively manages the challenges of high-dimensional optimization, leading to more efficient experiments and quicker discoveries compared to traditional methods.
That's an excellent analogy for understanding high-dimensional optimization. Moving on, could you explain how Bayesian optimization handles constraints in experimental design? What techniques are used to incorporate limitations while still aiming for optimal solutions?
Bayesian optimization handles constraints in experimental design like a skilled chef who must follow a recipe while also making sure to use only the ingredients available in the kitchen. The chef knows that certain combinations of ingredients will result in a delicious dish, but they also have to stay within the limits of what they can use. In the context of Bayesian optimization, constraints can come from various sources, such as physical limitations of materials, budget restrictions, or safety requirements. To incorporate these limitations while still aiming for the best possible outcome, Bayesian optimization employs several techniques. One common method is to adapt the model used for predictions to reflect these constraints. This means that when the algorithm evaluates different options, it considers what is possible within the given limits. For instance, if an experiment requires a temperature range that can't exceed a certain level, the optimization process will only propose solutions that fall within that range. Another technique is to use specific algorithms designed to handle multiple objectives along with constraints. This is like having a multitasking chef who can balance making a tasty dish while also keeping an eye on the cost and availability of ingredients. Moreover, Bayesian optimization allows for the exploration of solutions that not only meet the desired outcomes, but do so while respecting the constraints. This flexibility means that the process can still discover optimal solutions without compromising safety or feasibility. Overall, by effectively integrating constraints into the optimization process, Bayesian optimization helps ensure that the solutions found are not only optimal but also practical and applicable in real-world scenarios.
That's an excellent way to depict how constraints are managed. Now, could you elaborate on the concept of multi-objective optimization within Bayesian optimization? How does it facilitate the balancing of competing objectives? And what are the implications for experimental design when multiple outcomes need to be considered simultaneously?
Multi-objective optimization in Bayesian optimization is like trying to balance different ingredients in a recipe to make a delicious dish. For example, a chef may want to ensure that a cake is not only sweet, but also moist and visually appealing. In this case, the chef must balance these competing objectives to achieve the best overall result. When it comes to experimental design, multi-objective optimization involves considering several outcomes simultaneously. For instance, engineers may need to optimize for factors like yield, robustness, and cost. However, improving one objective might negatively affect the others, just like making a cake sweeter could compromise its texture. Bayesian optimization addresses this complexity by using techniques that allow for the evaluation of multiple objectives at once. It creates a model that predicts not just one outcome but several, helping to identify trade-offs between competing objectives. This means that when the algorithm suggests a solution, it considers how each option impacts all the objectives, allowing for informed decisions on which path to take. The implications of this approach in experimental design are significant. By incorporating multiple objectives into the optimization process, researchers can make better informed decisions that lead to more balanced and effective designs. Instead of focusing solely on maximizing one outcome while neglecting others, they can find solutions that meet various criteria effectively. This holistic view ultimately leads to more successful experiments and products that perform well across the board, rather than excelling in just one area at the cost of others.
Thank you all for joining us today. I hope you found this discussion on Bayesian optimization informative and engaging. As we've explored, Bayesian optimization is a powerful tool for experimental design, allowing us to efficiently navigate complex design spaces and make informed decisions. Key takeaways include: Bayesian optimization leverages Bayesian statistics to integrate prior knowledge and effectively handle high-dimensional optimization. It incorporates constraints to ensure practical solutions and employs multi-objective optimization techniques to balance multiple objectives. By iteratively refining a predictive model, Bayesian optimization reduces the number of experiments needed, saving time and resources. Remember, Bayesian optimization is a valuable asset for researchers and practitioners seeking optimal solutions in a wide range of fields. Thank you again for your participation and support.